Alright, so let's talk briefly about sex-linked diseases, right? So how sex works genetically, the genetics of male and female, okay? So we know that we have males have an XY chromosome and females have the XX chromosome, chromosome 24, the gonosomes, okay? So these are your gonosomes. Okay, this is male and this is female. So if there is a trait, right, which is carried by the X chromosome, right? The X chromosome carries, or the X gonosome carries a specific trait for, say, hemophilia, right? Let's say it's carried, so that's going to be an H there, right? Hemophilia. This is carried. This is recessive for hemophilia. So this gene, yeah, right? That's how we notate it. So if but we write it as a superscript, okay? So we'll say if the male has hemophilia, it'll be like so, right? But now let's say hemophilia is recessive, is a recessive trait. So in order to be hemophilic, you need to have 2H, right? So if you have a female whose genotype looks like this, she is a carrier for hemophilia, but she does not exhibit hemophilia because it is a recessive trait. So the dominant one, meaning no hemophilia, is there, right? Because hemophilia is recessive. If hemophilia was dominant, then by the mere fact of having the capital H there, she would be hemophiliac, right? So yeah, this is completely clean. So no, it doesn't even carry the hemophilia component, right? And this is a hemophiliac female, like this, small h, right? So this male does not have hemophilia, right? Now you can't put a Y, you can't put an H on the Y, because the Y chromosome does not carry hemophilia. Why? Because the Y chromosome is a shortened chromosome, right? Looks sort of like this. Normal, and then just like a little stub there. Okay, it's shortened. So it doesn't have the physical components where the gene is supposed to lay, where the allele is supposed to be found. It does not carry the allele for hemophilia because it doesn't have the physical space for where that allele should be. The locus doesn't exist because that arm of the chromatid does not itself exist, right? So that's why it's like that. So if we do a quick genetic cross, say we have a male who is a so the male, the father is hemophiliac, right? Hemophiliac, right? And the mother, the female, is a carrier of hemophilia. Carrier of hemophilia. So this would be our P1. Yes, you still need to write this down. And this is your phenotype. Okay, let's do a genotype. So the male chromosomes, we're now going to be an X and a Y. Okay, now on our X, the male is hemophiliac, which means we put a small h there, nothing on the Y because the Y does not carry the allele for hemophilia, the locus on which the allele occupies for hemophilia, right? And the female is going to be X, sorry about that. The female is going to be X because she's a carrier. We're going to have a big H and a small h, right? Hemophilia is recessive, so it's on the small h, okay? And now we have meiosis. We have gametes. Gamete formation. We get one XH. Right, we get, make that a capital X, please. It has to be proper. You know how these examiners can be, right? And we can have a Y. Okay. And then we have an X. Oops. X from here. And X from the female also, right? I just like putting the arrows to show where those gametes came from, okay? You don't have to, but it's nice to know, okay? So that's that so far. Let's continue. We have fertilization. fertilization, and we have our genotypes to follow. But first let's do a Punnett square. Okay, so we have X, H, Y. Okay. Books. And so we have an X, H, and X small h. Okay. Let's fill in the Punnett square. We get X big H, X small h. Get X small h, X small h. We get X, H, and Y. We get X small h and Y. So now let's write out the results of the Punnett square, right? As our genotypes. This would be the F1 generation, first filial generation. We have the genotypes. Okay, let's write this out. And then we interpret, okay? Alright, so let's identify what these are. So this would be a female carrier, because it's recessive, so there's a dominant no hemophilia. This is a female hemophiliac. Okay, this is a male clean, so clean male, no diseased, undiseased, okay, or healthy male, right? And this would be a hemophiliac male. So the important thing to understand is that it's impossible to obtain a male who is a carrier of hemophilia without showing symptoms. Why? Because you can either get this or that. You can't get, there's no big H small h, so there's no dominant one that can override a recessive carrier. So this male does not carry it, he just plain doesn't have it, right? If that makes sense. You can get a female, perfectly healthy female, yes, you can get XH, clean, completely clean for hemophilia, but this female here has a component of it. So while she carries it, she does not exhibit the symptoms. She's undiseased herself, right? This is perfectly healthy, no hemophilia gene at all. So you need to understand the male can't be a carrier because either they have a small h or a capital H. And if they have a small h, they're clean. Sorry, they're hemophiliac. If they have a capital H, then they are clean, right? Because of that Y. The Y doesn't carry any gene for hemophilia, so it can't carry the carrier, right? So that's that. Now while we're at it, let's look at how sex is transmitted. Why is it that there's a 50% chance of you being a male or a female? Okay, so let's say, let's do a genetic cross. So we'll say P1, okay, phenotype. In this case, the phenotype is sex. So we have male and female. Let's, down to the patriarchy, let's do female and male, okay. And then genotypes for each. Now the female chromosomes would be an X and an X, right? And male chromosomes would be a Y, an X and a Y, right? Then we have meiosis. Okay, after meiosis we have the gametes forming. So we have an X gamete, another X gamete. Okay, we have an X gamete here and a Y gamete, right? Cool. Then we have fertilization. Don't know what I wrote there, but just pretend it says fertilization. Alright. Yeah, in science you don't need to write the words properly or neatly. If you're saying, like, I don't know, what's this thing? Australopithecus, you can say Australo and then Pithecus, okay? Pithecus, right? So just start it off and then, yeah. Anyway, fertilization, and then we can do a Punnett square. So X, and we have X, Y, okay? So here we'll have XX, XY, XX, XY. So see, this is why we have 50% chance of being male or female, because here we write down of F1, first filial generation phenotypes, sorry, genotypes first, and we interpret, right? Genotypes, okay? It's going to be XX is to XY, so 50% chance of being female and 50% chance of being male, right? So phenotype, we'll say that same thing, male and female, okay? 50% male, 50% female, other way around. XY is male and female is XX, right? 50-50, that's the phenotype. That's why there's 50% chance of you being either a male or a female, right? So that was just some sex-linked characteristics. They are a bit more complicated ones. There are types where the disease is dominant, right? That'll be slightly different, right? So there can be diseases that are carried on the Y chromosome, but those are fairly easy to interpret because only the males would have them, right? But then now the other thing is that there's a higher chance of a female having the disease than a male, right? Why? Because the females can be carriers, because they have 2 X chromosomes, a male only has 1. So there's a 50% more chance of the male being hemophiliac than the female. Sorry, a female being hemophiliac than a male. Why is that so? Because the females X and an X, they have 2, because of the fact they have 2 X chromosomes, as opposed to the male just 1. They have nothing that can carry the hemophilia gene. So when a sex-linked characteristic for the X chromosome is recessive, the female, or even dominant, the female has more chance of getting it than the males, simply because there are more X chromosomes for which the disease to occupy. So either the male has it or they don't. The female can carry it. Okay, so females are more prone to diseases like hemophilia, color blindness can be sex linked, things like that, right? So in this case, color blindness, females, males would be more prone because I think it is a dominant trait. No, it's recessive, right? But I think it's males can get it more because males can also, it's either they have it or they don't have it. So females can be a carrier, okay? Actually, so in that case, right, males can't be carriers for a gene. So the female has the opportunity to be a carrier. So if there's a small h that is inherited, right? A small h is inherited. Okay, doesn't necessarily mean that the female has the disease, because this could be a big H, right? So they also have double the chance to not be diseased. So the percentages I gave you earlier was of carrying the disease. So yes, the female has a greater chance of carrying the disease, but actually being diseased? No, the males. So males are more prone to being diseased. Males are more prone to carrying the component which causes disease in them, because either they have it or they don't. Females can have it and have it be nullified by the presence of a dominant healthy gene. So males don't have that opportunity to override the unhealthy gene because they only have 1 X chromosome. So males, there's actually, males will die out first, right, in the long run, than females, and that's facts, because we can have more space for diseases without being overridden, and that's just some sex-linked things there. Next, we will touch on just a few other minor issues in genetic crossing, and then we can move on to a new section, right?